Welcome everyone. Welcome to our online class on Introduction to Deep Learning. And my name is Mihir Thakkar, the founder and instructor at Code Heroku. We at Code Heroku are trying to make world-class computer science and engineering education accessible to billions of students in developing countries. In our today's class, we'll be going over some of the key differences between AI, ML, and deep learning. So a lot of these terms have been used interchangeably by people who don't understand them well. Basically, I want you guys to be savvy about these, and then we'll study something about what lies at the heart of deep learning methods, which is called as a neural network, and which is inspired by human brain. A lot of you would have heard about neurons, and that's where the term comes from. So we'll see and talk about neural networks a little. This class is going to be a pretty much hands-on class. We'll just be spending first few minutes going over some of the introductory concepts in neural networks, and then just dive in and get our hands dirty with implementing a linear regression model in Pytorch. So artificial intelligence as such is not a new thing. Right from 1950s and even before those times, there have been mentions of scientists trying to create some form of artificial intelligence. In around 1950s, it was when something called as Turing's test, which was introduced by Turing. And he said that essentially if you could fool a human that you are not a machine, but another human, I'll grant you the stature of being an artificially intelligent agent. So, and the converse of that is also true, that if a machine can fool a human to say that no, it's not a machine, but it's another human on the other side, then by definition, the human becomes a machine and not a real human, if you know what I mean over there. But yeah, so it was a pretty philosophical, but yet something that people hold on today as well. And then around 60s and 70s, winter of AI came in. People said that these are weak methods and they don't really work in practice. So this is just waste of time. And then after 80s, backpropagation came in, and statistical learning methods started becoming more popular. And this was around the time of 2000s, when companies like Google, Nvidia started to heavily invest in machine learning techniques. The GPUs started becoming more popular. Machine learning researchers realized, I could parallelize my code and process it on a GPU to get the performance boost. And the same methods which were previously thought to be infeasible to be run on computers now started to become, they started working, because now you had the compute power to run those algorithms. And then after 2010, deep learning started becoming more popular again, because it was more feasible now with the extra compute power that we started getting. 2 days back, I don't know if a lot of you heard of this news, but these three folks got a Turing Award. Yeah, the same Turing that we heard of before. So it's considered to be one of the most honored awards in computer science for their work in neural networks and deep learning. That's how important this research is considered, because most breakthroughs that we have had in last 5 or 10 years in speech recognition, image recognition, all of those have been possible because of the use of deep learning. So this is what machine learning is essentially, right? So if you have a set of inputs X and you have a desired output Y, your task as a machine learning engineer is to come up with this mapping function F, which maps your outputs to, or your inputs to your outputs. So this is what machine learning and supervised machine learning specifically is all about. That's what we have seen so far. So you can draw a line, a regression line through all your data points. And we have studied in our high school class that you can characterize or represent this line using two terms. The first is the slope of the line, and over here it's the y-intercept. So if someone gave you these 2 points, that is what a machine learning model is in a 2-dimensional setting. So if you have more dimensions, this will become something such as a matrix multiplication of weights times your input vector. And of course, if you want to convert this to a classification problem, well, just add a sigmoid function to the top. You convert this regression to classification by just adding a sigmoid function to in front of this, but everything else remains the same. So now instead of getting a continuous output, you're getting either a 0 or 1. So your labels will be either blue or green, depending upon the input over here. So all good until here. What is the problem? Why are we thinking thinking something of neural networks or deep learning? Where is this need coming in? So the problem with this approach is, let's say you are doing something such as SVM, need an efficient representation of X to get a good result from your support vector machines or any other supervised machine learning algorithms that we have seen, is that you need an efficient representation of X. So let's say if you have a sound file and you give it to your SVM classifier, it is gonna just treat it like garbage. You won't learn anything. So you need an efficient representation of X in order to learn something meaningful. And that's what people used to do in older times. So let's say take a task of, so you have a apple over here and you want to categorize all your images as an apple or not an apple. So what people used to do in 1990s and 2000s is there was this computer vision expert who would create features out of these raw input files. So you could do something like thresholding, edge detection, and then you give this lower dimensional representation to your classification algorithm, and then it works, and a problem is solved. But the problem is this task of feature extraction is not that easy, and it's different for each problem. So ideally, what we would like to have is, can we take this apple directly and fed it to some kind of algorithm such that it learns all the features by itself, and we don't have to do this task in between for every new problem that we come up with. So that's a challenge which a human brain has solved over a period of our evolution. And the way it works is, so what we could do as machine learning engineers is take some inspiration from this biological setup that we have within us. So what we see in a human brain is there are a lot of neurons who kind of talk to each other. They seem to pass electrical signals from one neuron to another through a thread-like, a mesh-like structure. And depending upon how much input or how much electrical impulse a neuron gets, it either fires or doesn't fire. So how do we represent this system which is inside our head in a computer, or how do we model this? So few smart people came up with this. So they were like, okay, it seems like there is one central element to it. Let's break it down. There is one element, a neuron, which takes in several inputs. So let us do something like this. So there is one neuron which takes in several inputs, and there seems to be some weights associated with these connections. So not all threads are equal. Some connections are strong, some connections are weak. And that's why they said, okay, there are some inputs and there are some weights associated to each of these connections. And the output at this point, Z, will be nothing but addition of all these inputs that I get. So based on the signals that I get from my neighboring neurons, I'll add all the signal up. And next, me as a neuron, what I'll do is I'll check if this input is greater than certain threshold. So this Z over here, which is the output over here, is greater than some threshold, I will fire. Or if I'm less than, or if this Z is less than certain threshold, I won't fire. So that's what the output equation over here is saying, that Z is summation of all Wi times Xi. So you just take all the inputs, multiply them by their weights. That will give you Z over here. And based on this sum, then I'll ask myself, is this Z greater than certain threshold? If yes, I'll fire and I'll pass the same signal to some other neuron. And that's how you can model this system, which is going on in our head. And again, this is not a very good model, but that's the best that we have been able to come up with until now. So if you think that you can represent what's going on inside your head in a much better fashion, well, maybe a Nobel Prize is waiting for you. You should try and model that out and see if those kind of neural networks that you make work better than what are already existing. So Divya is asking, what do weights represent? So the weights over here are representing the connections between these neurons, the strength of the connections. So we know that there are some connections between these neurons, but there are all connections are not the same. Some connections are stronger than others, and that's what these weights are representing over here. Does that make sense? So a bias for a neural network over here is this threshold. So once you pass this threshold, you are firing. If you don't pass that threshold, you don't fire. So that's what the threshold is. So, and a lot of times what people do is, instead of modeling it like this, you could give another input which is coming in, and you call that as bias, and eventually the end result will be the same. So if you work the math out, you will get the same equation over here. So how does this help? Why is this any different than other methods of supervised machine learning? So it seems like it is doing the same thing, but it's automatic. We don't have to extract these features by ourselves. Or these are the weights that were learned by layer 1. These were the weights that were learned by layer 2, and so on. So this is one visualization of the weights inside a neural network. At the first layer over here, so imagine that this is the first layer of neurons, and then so on. So in the first layer of neurons, this is an example of where we are visualizing these weights, these WIs, which are learned after this system has learned how to recognize images or classify images. In the first layer over here, the network seems to be identifying these small patterns or these miniature patterns and textures in our data set. And slowly, as we go from layer 1, layer 2, and so on, we are getting bigger features. Or the way you could also think about is, we are classifying images based on minute details, and then over and over, we are classifying them with more abstract features. So again, how did we make our lives easier? A person had to sit over here and manually write feature extraction techniques, use feature extraction techniques to extract key features from our raw data set. But this was tedious, and we had to do this for every new problem that we came up with. So coming up with features for images was not same as coming up with good features for sound files, and so on. So how did we solve this problem? With neural networks, what we are seeing is you could feed in raw data files, and inside the layer itself, inside different layers, it will learn different features, and starting from more detailed features like textures and colors, it will go on, and at the end you would see that this layer has learned more abstract features and essentially would be able to classify images more accurately. All right, so let's get over here and let's do some hands-on session. Let's get into our hands-on session. So what I'm going to do is I want you guys to go on notebooks.azure.com, and create an account for yourself if you don't already have one. So please go over here, notebooks.azure.com. Once you are over here, say sign in. So I already have an account over here. So if you don't have one, you can say create one, and we reach to this point. So wherein I am logged in. Let's click on my projects, or it says you have no projects. Would you like to create one? You could click over here as well. Click on create one now. We need to create a new project. So say create one now. I'm gonna call my project as, you can call something that you would like, but this is like a first introductory. I want to have it public and initialize this project with a README. So I'm gonna just keep that as is. Just say create, and gets me to this point over here. Once you are over here, let's just say run on free something something, which they don't show. So run on this, so hit this run button. And we have our Jupyter notebook running in the cloud. So I'm gonna save this notebook. So I'm gonna rename this as linear regression, because today we are going to solve a simple linear regression problem using a neural network. Okay. Copy this entire thing, Control C, go to your notebook and paste it over here. Yeah, so works for me. Let me know if you were able to do that as well. So hit the run button over here to run the first cell in your notebook. And guys, there is no rocket science over here. What we are just doing in this cell over here is saying import Pytorch that we are going to use to build our neural network, and matplotlib, numpy, and we just have a training data set, which, let's go ahead and visualize this training data set. So I'm just going to say plot. I'm going to say x train, y train, and I want the rounds over here, and run this one. And this is what the training data set looks like. I'm assuming that by now you guys know what a linear regression is, and we are trying to use a neural network to solve the linear regression problem. All right, so the next thing that we will do is so over here we have a numpy array, which is for x train and y train. We need to make it in a form which is more suitable for our neural network to use. Pytorch gives a bridge between our numpy arrays and our neural network. So what we'll say is inputs equals to torch dot from numpy. So this will create the neural network input layer from this numpy array, and we'll just give it x train, and I can say targets is equal to torch dot from numpy y train. So I'm not doing anything crazy over here. So next what I'll do is create a linear regression model. And so what I'll say is model is equal to, now we are already importing the neural network over here from torch.nn. So I'm saying nn dot linear. Now this is not same as saying create a linear regression model, but I'm just saying create a simple linear layer. I'm just creating one layer over here. So how many features do we have and how many target variables? So yeah, one feature variable and one target, right? So I'm just going to say 1 and 1 over here. Okay. So I'm just saying that there is one input node and one output node. Well, when we were doing gradient descent or whenever we do any supervised machine learning algorithm, we try to make some predictions, and we are also given the actual answer of that result. So what is the error that we calculate and what do we try to minimize? So Jay says actual minus predicted. Yes, but do we use it directly, actual minus predicted, or do you take some form of absolute values by squaring those results up? Yeah, so you use something like mean squared error. So what I'm going to say over here is the criterion based on which I'm going to determine how well my network is doing will be neural network dot mean square error. Okay, and there are other criterions which are available in the library. You can go and look it up. All right, so the next thing that we will do is to calculate our gradients. Again, we are gonna use the gradient descent to minimize the loss. So what is this saying? So this is saying that when I created a model, it has initialized this model with some random weight, and this weight is minus 0.147. So this is a random weight which it has initialized with. So we want to come up with the m and the b of this line, the slope and the y-intercept. So this weight over here is the m, or the parameter of that line. So right now we are saying that we have initialized this line on a random weight, and this weight is minus 0.14. And our task is to come up with better values of this weight by doing gradient descent and adjust the network weight so that we have minimum error. Does that make sense? So we have a random weight, or the random m, that we have selected for this line over here. And in next few steps, we'll be using gradient descent to optimize these weights and come up with a better weight for our for the linear regression problem that we are trying to solve. Perform gradient descent, the first thing that we will need is some form of an optimizer. Optimizer is equal to, now you might think if you are new to Pytorch, this might look a little bit of black magic to you, but trust me, once you get used to it, you'll feel like, no, these are the standard things that you do always. And there is an optim package over here, and I'm going to use a stochastic gradient descent optimizer, and I need to pass all my model dot parameters over here because it has only two parameters over here. One is the weight, and let me also show you this guy. So we also have print model dot bias over here. Is it bias? Yes. So these are the two parameters of our model, the weight and the bias, and we're just passing it to the stochastic gradient descent optimizer so that it can optimize these two parameters. Easy. Someone was telling me that they are getting an error that the learning rate is not defined. So let's go ahead and define the learning rate of this optimizer. Let's just use a small number, something like 0.01. Okay. And run this. So we have our optimizer defined now. We haven't done anything with it as such, but we have it now. So I saw a question over there saying, what is the SGD, or the stochastic gradient descent method? So I strongly refer you to our previous videos on gradient descent, where we did an entire class on what gradient descent is, and stochastic gradient descent is just the most simplest form of gradient descent, where you adjust your line based on the error that you get for each point. So after every point, you check the error and you say, okay, let me adjust my line a little bit. Let me adjust my line a little bit over here. And that's what you do. And over here, we are using the stochastic gradient descent to optimize the loss or to minimize the loss. Let's do the first pass of our network. So we are going to call this as forward pass. You can make sure it is commented. We are just saying that we'll pass the inputs to the model and we'll get some output. So what we'll say is model inputs, as simple as that. So we're just passing the inputs to our model, and let's capture it somewhere. So let's say outputs is equal to model inputs, as simple as that. So once we have passed our inputs and got some output, what will be the next step? So we started off with random weights, random weight and a random bias. We passed our inputs and got some output. What should be the next logical step to perform over here? So how do you adjust? Like how do you become better? First, you need to calculate the loss, right? How much wrong you are. Once you know how much incorrect you are, then you can adjust yourself, right? So let's calculate the loss, and the way we'll do that is we already defined a criterion over there. So I'm going to say loss equals to criterion, and what should be the two things that I should pass over here? What are the two things that we pass to the mean square error? Yeah, the test and the predicted values, right? So in this case, our predicted values are the outputs. And what are our actual output, or no, what is the expected output? What variable has that our expected outputs? Yep, the targets. So difference between these two will give us a sense of what is the loss in the network right now. All right, so the next thing that we should do over here, after we know how much the error is, now we need to optimize it. So we need to say, we need to do a back propagation. So we need to perform a back propagation and optimize. So what we will do over here is say optimizer dot zero grad. So again, these are standard things that you will become used to. So right now it might seem like black magic. Back propagate the error that you got through each node, each neuron, and then let's optimize it. So I'm going to say loss dot backward over here. So this will propagate the losses to each of my neurons from my output towards the input, and then just say optimizer dot step. So it's just like incrementing it, just saying I'm done with one step of optimization. All right, so once we are done with this, let's plot our predictions. So we completed one round of optimization. So let's plot it and see how well did we do. So I'm going to say y predictions is equal to, and we want to convert it to a numpy array. So I'm going to say detach numpy. So let's plot these two things. First, I'll plot the same graph that I plotted before, which was x train comma y train, the same dots that we had, right? And then I could say red dots over here, and let's say label is equal to original data. So these are the points that we already plotted. So same thing. So I'm just saying use red dots and add a label as original data. Then we can say plot x train, but this time I'll say y predicted, because now I want to also see how are our predictions like, and label is equal to the model. So seems like in one pass of gradient descent itself, we came up with a kind of good approximation of our model over here. Right, so let's also go ahead and print the loss that we have in the step over here. So let's come over here and say, so this loss over here, if you want to print it out, you could just say loss.item. Now I'm getting a loss of 0.43. Okay. So let's run it again. What happens? And now the loss is 0.35. Right. So we are actually getting better results as many times we run this. So run it over here. Let's run the graph again. And even though visually it is not possible to see it right now, but over here we are seeing that the loss is definitely reducing, right? So instead of just doing it once, what if we want to do these steps multiple times? What can we use over here to perform the gradient descent multiple times? A simple construct that we could use to just execute this block several times. What should I write over here? Well, we could use a for loop over here, right? Yeah, I mean, we could either create a function or just create a for loop over here. So I'm just gonna say for I in range. You could try it many times, but let's say I'm going with 60 over here. And you should see that after a point, your loss is not decreasing. So you could change the number of iterations that way. All right, so I'm just gonna say this. And let's try to run this several times. And as you see, after a point, you're not getting any better results and you could also print out the learned weights of the model. So you could say print model dot weights and print model dot bias. So now these are the weights that we have learned. We started off with random weights and a random bias, and these are the weights that we have learned after performing the gradient descent optimization on our network. Oops. So guys, let me know once you are done if there is something that you did not understand. That is what we had in the class for you today. It was pretty. So thanks again for coming. I hope you had a good time in the class today and something new that you learned. If there are any feedbacks, please send it to me. If you are on the WhatsApp group, you could send me over there. If you are not part of the WhatsApp group, you should join it definitely.